It is August 21st, approximately 7:41 a.m. And we're going to be going over preliminaries from Dummett and Foote's textbook on algebra. Should be rather interesting. And I want to start off with, well, let's put that up here, what we're covering. Chapter 0, it's not an actual, chapter in this book really, but that's just what we'll call it. There's a whole algebra textbook called Chapter 0 that starts with category theory and so on, but we'll just use Dummett and Foote because that seems to be the accepted, almost monopolistic standard, but it's kind of just a earned monopoly in a way. Okay, historical context. The concepts in this section, sets, functions, and relations, are so common now that they can feel obvious, but each idea has a history, and you can even look at the math history that I went over in length from Boyer and Murbach's textbook. But sets, ancient mathematicians grouped things, all even numbers, all triangles of a certain kind, right? Without naming the concept. In the late 19th century, George Cantor defined sets formally and introduced symbols in a set, proper subset, the order of a set, for membership subsets and size, functions. In the 18th century, a function meant a formula. Dirichlet, or Dirichlet, in 1837 redefined it as a general rule, pairing each input with exactly one output. People long used, with relations, people used ideas like something has the same remainder or is the same shape without a more formal mode of abstraction. By the early 20th century, the notion of a relation was formalized within set theory, leading to the powerful concepts of equivalence relations and partitions. Now, in this section, we'll establish the exact definitions and notation for these ideas so that later topics can be expressed with full, rigorous precision. Just check that. So, that is not the best eraser. Or maybe it's just not good for it. Maybe it's a combination of something. Okay. So a set, it's a collection of distinct objects called elements or members, roughly speaking. We'll just call them elements. Some of the notation for this, for some this may be more obvious than for others, so just write it out here. That means X is an element of A. Naturally, this means X is not an element of A. This means that every element, forgot to write the A here. This means that every element of B is an A. B is a subset of A. I seem to have misspoken earlier, I think. I think I said that this meant proper subset. No, that just means subset. This means proper subset, no caveat. B is a proper subset of A such that B does not equal A. Simple enough. Empty set. And this refers to the cardinality, the number of elements. So you can kind of see the approach we're having here, starting with the basic elements of the thing. And in this case, the number of elements. Right? So if A is finite. So that's just general set notational stuff that we'll be using consistently. Check that again just to make sure. That's better. Okay, so now we have this thing called subset. Subset by rule. Everybody knows what subsets are, right? Well, if you don't, we can just write it out here. We can describe a subset of A by giving a condition. So B is equal to the set of A in A such that condition on A. For example, if A is equal to 0, 1, 2, 3, the set 0, 1, 2, 3, then B, being the subset of n within A such that n is even, gets us elements 0, 2, 0, and 2. All right, another thing, Cartesian product. So we have sets A and B. Then the Cartesian product A cross B is equal to the set ordered pairs made up of A, B, such that A is within A and B is within B. Little a within big A, little b within big B. So, for example, say A is equal to 1, 2, set 1, 2, and B is equal to x, y, then we of course have A cross B is equal to 1x, the ordered pair is 1x, 1y, 2x, 2y, very good. Moving right along. Get faster I move along, the faster we can get to the actual substance of the thing. But preliminaries are preliminaries, you know. It's a good little freshen up and remember sort of thing. Functions, also known as maps. A function, f from A to B, assigns exactly one output in B to each input of A. So for this, there's the domain A, which is the set of allowed inputs, codomain set where outputs live, value at A, which is f of A. All this makes sense. So suppose we had that A is equal to 0, 1, 2, B is equal to 1, 3, 5, 7, f of 0 is equal to 1, f of 1 is equal to 3, f of 2 is equal to 5. That could very well be a thing. Now, there's this notion of an image or range. Now, the image of f is f of A. It's defined as f of A is equal to the set in which little b is in B, such that B is equal to f of A for some little a within big A. For example, in the example earlier, f of A, shouldn't have erased that so quickly, but remember we had f of 0 is equal to 1, f of 1 is equal to 3, f of 2 is equal to 5. F of A in that example be equal to 1, 3, 5. Right, so let's clarify. Pre-image, also known as the inverse image. So for C as a subset of B, the pre-image of C is defined such that for the inverse, f of c equal to a within a, little a within a, big A, such that f of a is within c. Now, if we were to have c is equal to 3/5, then with what we established earlier with our previous example of f0 equals 1, f1 equals 3, f2 equals 5, say that c equals 3 and 5, then of course the pre-image is equal to 1, 2, right? So you can see that pretty easily right there because boop, boop, it insists upon itself. Now, there's also this notion of a fiber over B. Now, the fiber over a single B over a single B within large B, the set B, is F, the pre-image of the set, the singleton set containing little b. The set of all inputs matching up to little b. Just sort of mention that real quick before turning to this next valuable piece of information, which is special types of function. Functions, injective, also known as one-to-one. A1 not equal to A2 implies f of A1 is not equal to f of A2. Sub A sub 1 is not equal to A sub 2 implies f of A sub 1 is not equal to f of A sub 2. Now, oops, I'm not going to erase that yet. Surjective. On 2. Every B within B has some, every B within the set B has some A within the set A with f of A equal B. And there's nice diagrams of this as well, by the way. You can look at that. It's pretty nice, assuming you haven't seen this before, which is, kind of laughable, but, refresher, like I mentioned earlier. Bijective, which is just to say both injective and surjective. Which, this is just a thing that's, I shouldn't say obvious, but it's kind of like, it's really clear that there exists, that it has a unique two-sided inverse. Now, we mentioned earlier, so we've covered the basics of looking at sets, the basics of looking at functions. Now we go back to that third thing which we mentioned in the historical overview, which of course is relations. So a binary relation R on a set A is a subset of A cross A, and we write this as A R B if ordered pair AB is within R. It's within that binary relation. An equivalence relation a fancier thing. It has three properties. And these are, of course, reflexive, which is such that A R A for all A then set A. Symmetric. ARB implies that BRA. Sort of see, symmetric, that's just kind of very intuitive. Transitive. It's kind of like syllogistic. ARB and BRC imply ARC. No, the A's are A's. They're not C. Stupid joke. Okay. Now, equivalence classes. Let's go a bit more in depth into that. So, for A within A, the equivalence class that it's not a curly bracket, it's just brackets, is equivalence class of A is equal to the set X within A such that X are A. Any element of an equivalence class is called a representative of said equivalence class. So in a way, it's a very special kind of it's a very special set, in a way. In a way, no, I think I could say it like just literally. Any element of an equivalence class is called a representative A representative, of course, is assigned to the government with regards to proportional population of each state. No, but suffice to say, it's called a representative of said equivalence class. Partitions. If anybody has a hard drive, you know, you can partition the thing. Partitions isn't just a math term, so it's kind of, you know, more intuitive than I think equivalence classes would be as a term. Partition of A is what? Is a collection of non-empty disjoint subsets whose union is A. So equivalence relations or partitions are two views of this same structure. The equivalence classes of an equivalence relation form a partition. So let me go ahead and jot that down as a note. I guess you could kind of say they're two sides of the same coin, right? They're two ways of describing the same phenomena here. The equivalence class is, there we go, of an equivalence relation form a partition. And what? And any partition defines an equivalence relation. It's kind of this notion of a rough correspondence, a rough equivalence that we'll get into later, that this is kind of foreshadowing in a way. Equivalence classes of an equivalence relation form a partition, and any partition defines an equivalence relation. So let's look at a proposition, right? I gotta bring a whiteboard eraser spray next time. So, proposition 1, which I'll call prop 1. Ready, action, you know, it's a prop. Okay, so let's characterize interjections, surjections, bijections via inverses. So let's suppose that f is the map from A to B. Let's let that be a function. So, f is injective. F is injective if what? Well, it goes two ways. If and only if f has a left inverse. So, such that there exists G such that B to A, G, mapping G from B to A such that with the composition of G of F, we have the identity of A, identity sub A. What else? F is surjective. Ooh, this is going to need a lot more room. Okay, so F is surjective. What does that mean? If we're speaking inverse talk, right? Sounds almost Orwellian, but F has a right inverse. F has a right inverse. There exists H, which maps B to A, with the composition F of H equal to the identity of B. Wrote too big, so now I'm paying the price for that. Okay, so F is bijective. It's both of these things, right? So if F is bijective, well, F is bijective if and only if there exists G, which maps B to A. You know, it's both of these things combined, right? So a composition F composed with G is equal to the identity of B, and G composed with F is equal to the identity of A. So in this case, there is many good things in this case, trust me. No, but G is unique and equals preimage, the inverse of F. How does that show up? Yeah. Well, let me just put another thing over here on this side. Hopefully you can see that far. Yeah. If A and B are finite, with the cardinality of A equaling the cardinality of B, number of elements, then F is injective if and only if F is surjective if and only if F is bijective. Just sort of see how that reasonably might flow, but there, of course, is a proof to get to for this. Well, let's look at the proof. Start with 1, right? So let's take a step back. Assume F is injective. So if we assume that F is injective, then by definition, for each B, within the set B, I mean to say, if there exists A within A with F of with F of A equal B, define G of B equal to A, and this A is unique by definition, by injectivity. Now, if no such A exists, define G of B arbitrarily in A, such that we choose a fixed A naught within A. Then, for every A, within A, the set A, we have F of A in the first case, so G of F of A is equal to A. So G composed with F gives us the identity of A. Very good. Okay. Now, for the other way around, let's suppose there is a mapping G from B to A with G composed with F equaling the identity of A. Well, if F of A sub 1 is equal to F of A sub 2, then applying G gives A1 is equal to G composed F of A1, which is equal to G composed with F of A2, which is equal to A2, which means that by definition, F is injective. So one's good. All right. Let's assume, for 2, let's assume surjectivity. Let's assume F is surjective. If F is surjective, then for each B within the set B, we can choose some A sub B within A with F of A sub B equaling B due to surjectivity. Now, let's define H of B to be equal to A sub B. Then, as a consequence of that, F composition H of B is equal to F of A sub B, which is equal to B for all B. And so, F composed H here gives us the identity of B. I guess I could just say, F composition H. I don't have to say the whole longer thing. Yes, okay. Now, let's see. Check that. Composition is equal to, yep, okay. Now let's go the other way. Now, if there is an H with F composition H equal to the identity of B, then stands to reason that for each B within the set B, we have B equal F composition H of B equal to F of H of B. So B lies in the image of F. From that, we have that F is surjective. Now let's move on to 3. Oops, I erased the proof there actually. And so let's suppose that f is bijective. F is bijective. Well, if f is bijective, then it has two-sided inverse. Preimage of f inverse from B to A with f composition f inverse of f, I mean to say, is equal to the identity of B. Stealing that is no joke. And preimage of f composed with f is equal to the identity of A, which is, of course, standard inverse of a bijection. Now, conversely, if there exists G with both identities, then by one, that being, of course, the proof of one that we had earlier, well, that property of the proposition, which we did prove by 1, that being the thing we referred to, f is injective as it has a left inverse G, and by 2, f is surjective. As it has a right inverse G. So, putting these together, of course, what do we get? Well, it's two-jective, it's bijective. Put that on a Twitter handle. Okay. So, there's also this other thing, which I should mention, this other thing that's part of this. It's very important. Uniqueness of the inverse. Now, if G sub 1, G sub 2 both satisfy, or are maps from B to A, which satisfy F composition G sub I is equal to the identity of B, and G sub I composition F is equal to the identity of A for I equal to 1, 2, then we have that G sub 1 is equal to G composition identity of B, which is equal to G composition F composition G sub 2, which is equal to G sub 1 composition F composition G sub 2, which is equal to the identity of A composition G sub 2, which is equal to G sub 2. So they are in fact the same. The inverse is in fact, this is, yeah, so there can only be one because, we checked it such that if there are two such that this property holds, well, we find that there's actually one, and so there's one. Let's check that. Yep. Oh, and I didn't draw the little arrows before, but should have been picked up that, conversely, and first those things follow the same pattern, so that's fine. And that last bit which we haven't proven yet from the proposition, see here, yeah, finite. So assume cardinality of A is equal to the cardinality of B, and that both of these things are not infinite. They are in fact finite. Well, if F is injective, then no two elements of A map to the same element of B. All right, that's the definition, practically. With cardinality of A equaling B, the cardinality of B, we have that this forces F to hit all of B via pigeonhole principle, which we'll get into a moment here. So we then have that F is surjective. Conversely, if we have that F is surjective, then we have the mapping the number of elements, the cardinality number, the number of elements, the cardinality of A elements onto B is equal to cardinality of A elements forces no collisions. Which means that F is injective. We'll go into a bit more of what this means here in a moment. I think, yeah, pretty sure we covered pigeonhole. Okay. So, therefore, which by the way, symbol for therefore is these three dots in the shape of a triangle, an implied triangle. Therefore, injective if and only if surjective with either implying bijective in the case of finite cardinality. Okay, very good.